Today, 14th October, we have to do chapter 22. Monitoring and control systems. Learning objectives. By the end of this chapter, you should be able to show understanding of the difference between a monitoring system and a control system. Though they look similar, you will find, though you are learning a new thing, though it's similar, there is a difference between the two, monitoring and control. Show understanding of sensors and actuators and their usage. Show understanding of the additional hardware required to build these systems. Show understanding of the importance of feedback in a control system. Show understanding of the software requirements of these systems. How bit manipulation can be used to monitor and control a device. Carry out bit manipulations. Show understanding of how to make use of appropriate bit manipulation in monitoring systems and control systems. Logistics. Monitoring can be used to describe a very wide range of activities, but all are characterized by the measurement of some physical property. Typical examples of the physical property could be temperature, pressure, light intensity, flow rate, or movement. There are many more. These are just a few to mention. Let's consider temperature as an example. If this was being monitored under human control, the measurement could be made with a standard mercury thermometer. However, in this chapter, we are interested in systems where a computer or microprocessor is being used. In this scenario, monitoring requires a measuring device that records a value which can be transmitted to the computer. Such a measuring device is called a sensor. For monitoring temperature, a sensor could contain a thermocouple which outputs a temperature dependent voltage. What happens is the slight temperature, the temperature will generate a slight voltage depending on the temperature. High temperature, high voltage. Low temperature, low voltage. Just imagine like that. So when you have this device or the sensor to measure the temperature, it will generate a small slight signal, an analog signal for that matter. Keep that in mind. Later you will come across the implication of analog and digital signals here. There can only be one of two reasons to monitor a system: to check whether or not the monitored value is within acceptable limits in a safety system. If the measured property has reached a dangerous level, some immediate action is required. So in safety systems, these are used. To ensure routinely and continuously that the monitored property is as required. If the value measured indicates that a change has occurred, then the control part of the system may have to take measures to reverse this change. Excuse me. So first is for safety, and the next one is to maintain a continuous flow of a process. For example, in a chemical process, in a lab, this is important to have the temperature constant or some other property. What are the other properties? We learn physical properties like temperature, pressure, light intensity, flow rate, many things. The control element of a monitoring and control system needs a device called an actuator. So this monitoring system is just monitoring and letting the humans know about some danger or something or change in the property, this measurement. But a control system will also correct if there's something wrong, automatically it will correct the situation also. To do that physically, you will need a output device called actuator. This actuator only will switch on something, switch off the cooler, switch off a tap, open a window, things like that. As an output, you need the the system needs a thing called actuator, a device. 22, the figure 22.01 shows a schematic diagram of a computer controlled environment. So the key terms are sensor, a hardware device that measures a property and transmits a value to a controlling computer. An actuator is a hardware device that receives a signal from a computer and adjusts the setting of a controlling device. So as we learned, a sensor acts like an input device, generating a signal and sending to the microprocessor, and the actuator is like an output device. Figure 22.01 includes an analog to digital converter. That is because the sensors produce analog signals, but the processor cannot process or accept or understand analog signals. Processor works in digital, so it has to be converted, and that is called the ADC, digital converter, and a digital to analog converter, reverse of it, DAC, as separate components, but they are likely to be integral to the device in the controlled environment. So same way that the analog system has to be converted to digital in order for the processor to understand, the processor issues outputs to an actuator in digital form. And the actuator, in order to open a window, close a window, or open a tap, close a tap, stop the cooling motor, heater, various things, needs analog signals to work. So therefore, the reverse of it happens, digital to analog, and that's called the DAC. It should be noted that the diagram also shows an actuator as a single component. The actuator as a single component. So in the actuator like a single component, it shows. This is a simplification. An actuator is an electric motor that drives a controlling device which is not shown. So this is only like a symbol to show what it is. The working and the details are not shown here. The system shown in figure 22.01 involves a continuous process where a measurement is made and then, if needed, a control action is initiated. Following this control action, a measurement is taken again. There is therefore an element of feedback in the system, like a loop. The sensor senses something, some signal, and then analog measured value. Then the ADC converts it to a digital, sends it to computer or microprocessor. This is now converted into digital. Then the digital control signal to the after processing is when the computer or the processor issues a signal to the actuator. It goes through the DAC and then converts back to analog control signal so that the actuator can finish it. But it doesn't end there. The process doesn't end there. In a controlling system, it goes again. For example, this actuator is correcting the situation of the property, the required property that the sensor is monitoring, sensing and sending. So the computer will have some stored data, will compare with that and correct the situation. So actuator outputs, for example, if it is um, humidity, let's imagine that it's a humidity control system in a greenhouse. So here, if it is too dry, the sensors it's too dry, and depending on the stored values here, how much it is. If it exceeds that limit, then computer will issue a signal to open a tap, a sprinkler, to open a sprinkler so that water will be sprinkled inside that greenhouse and the humidity will be increased until again this will send. Now when this is changing now, the humidity here is changing and then the sensor is continuously sending the measurements. Then it will stop at one point. The computer processor decides that okay, this is the exact amount I'm required to stop this. Then issues the signal to close the sprinkler. That is how it works. So feedback is called the feedback. It's very important. A closed loop feedback. It's also called a closed loop feedback. Control system is a special type of monitoring and control system where the feedback directly controls the operation. Figure 22.02 closed loop feedback control system shows a schematic diagram of such a system. A microprocessor functions as the controller. This compares the value for the actual output as read by the sensor with the desired output. It then transmits a value to the actuator which depends on the difference calculated. So the desired value for output is stored somewhere here. Controller can always compare. The sensor gives the value to the controller where it's done by a microprocessor, compares this and sends a signal to the actuator to do something, to some process to correct the situation. And the actual output is there. So the output actually affects the input here. The output affects the input here. The next input is affected by this output. So it's like that closed loop feedback control system. Real-time programming. Any questions, Shaida, up to that?
No, sir.
Okay. Then real-time monitoring and control systems require real-time programming. Whether a program is just monitoring or is monitoring and controlling, it must incorporate a structure for repetitive sensor reading. So it cannot wait, like it has to be real time, meaning instantly. Otherwise, it will be too late in a system like this. This must continue for the whole duration of the period that the system is switched on. A simple loop structure will achieve this. But reading sensor values every clock cycle of a processor is unnecessarily frequent. The program must control the timing of the repetition. This might be done by creating a timed sequence for reading values or possibly by including a time delay inside a loop. The idea is this: the controller, which is a microprocessor, the pulse rate is very high, very high. It's not necessary to check with every pulse, the clock pulse, with every clock pulse to check the temperature or pressure or whatever it is. So how do you delay it? How do you delay it? By this program code. You have to have a timing structure. Uh, this might be done by creating a time sequence, reading value, or possibly by including a time delay inside a loop. You know that in Python or any language, it can be delayed. A certain thing has to be delayed, like timing. So every 1 minute, every 5 minutes. How do you do that? Have a loop. Mm, A is uh,
Um,
and we want to print, right?
Print.
And just say while A is, I'm just thinking, while A is less than 100, mm, then that we only want to count only 10, right? Print A. Do you see anything wrong in this?
Mm, no.
Invalid syntax. Very common mistake. Forgot to increment. Start with 1 and then increment, right? A equals A plus 1. It, run it. Okay, so 1, 2. But it's very quick, no?
Mm-hmm.
And see, it's like instant, no?
Yeah.
That comes. But in case if we want to make it slow, then
Yeah.
after printing the number, we have to delay. So what I'm going to do is B, B equals 0. B is less than 1 billion, no? 1 billion. Uh, just add it, like B equals plus 1. You know, we are not doing anything, any output. We are not doing, just counting, just counting up to
Okay.
1 billion.
Okay.
Then do the normal thing. Let's see what. reinitialized. Becomes 1 million, yeah. Ah, okay. So every time it comes zero, small one, maybe 1. There was a delay, no?
Yeah.
Notice. Now let's make another zero. See, so this is the way you use the programming code to delay. So if the temperature sensing is like earlier, if it is so fast, temperature doesn't change quickly, no, due to some process or heat or light, the temperature time to change. So
Yeah.
in that case, it's a waste of time in every pulse. So here, at it again, do you understand it? This is a normal process. Yeah, only this printing A, the value of A from 1 to 10. That process. 1 to A, so that at 10, it will start printing 10. But we want to delay this. It's like, hide and seek, the catcher. What does he do? She closes the. Have you done that? She closes the eyes and then counts up to 10 or 100 until the players go and hide. You know that game?
Yeah. Yes.
So that
Yes.
is something like that, delaying tactic, so that the others have time to hide. Same way here, this is also delaying tactic. All right. So this is important in many programs. You will need this when you become a professional programmer. Yeah. Uh, this might be done by creating a timed sequence for reading values or possibly by including a time delay inside a loop. So we are using a loop, get in the computer, tell the computer, okay, count up to 1 million, then do the next one. But of course, it's so fast. Hmm? In a second, it has counted 1 million. We, of course, will take, in about 1 second, we can count up to about 3 or 4. No? Or
Yeah.
that's all. Then the extension question 22.01. Research the capabilities for controlling the timing sequence for continuous running in your chosen programming language. Which ones would be best suited to a monitoring and control program? Here is an example monitoring program. Consider the following fragment of pseudocode. Fragment, yeah, only a piece of it, not the full program. End reading sensor. Hmm. There is a, let's say, we have a like a flag like this in reading sensor, like a value. We make it false at the beginning. Reading out of range also false. Those are the initial values we give these two variables. Then we repeat, we start a loop, call sensor read sensor value. So this is not in our program here, maybe at the somewhere else. Now here at the moment we don't know, but we only know that this has some coding which will run when we do this. When you say call and give the name of the function, when we created the function, that all the instructions will take place. If sensor value Now after getting the sensor value, now this is the sensor value returned by this function, which means in short, in simple words, a sensor sends a value to the processor. Now this is the work of the processor. Processor is checking if sensor value is greater than maximum allowed. So maximum allowed is stored here. Desired value for output, that's a value there stored. So the microprocessor constantly checks and compares. If the sensor value what you receive now is more than what is allowed, maximum allowed, then reading out of range, true. Reading out of range, true. Because earlier we made it false, no? Now we make it true. Then reading equals h, high, low. So we give another value to another variable called reading. Else, if it's not, that means it's within the range, within the accepted range. Then sensor value, if sensor value less than minimum allowed. So there's a minimum also. There's a maximum and then a minimum. That's how a range is defined. No? Then if that happens, again, reading out of range equals true. So this becomes true either if it is more than a particular stored value or less than the particular thing. But if the thing is minimum allowed here and they are maximum allowed, two values. So then you make it reading out of range equals true and then reading equal L. So the same variable reading is L here, reading is H there. So that we can make use of that variable later to see whether it's high or low. Why? Because if it is high, you might have to, say for example, put water or something. If it is low, then you might have to open another heating motor or heater or something like that. So things like that, we flag it here. Because of this, we know later on, the program will know what to do. If it was the same action required in either case, then of course you will not have H and L here. Because no use. No? For H also the same action, L also is the same action, then you do not have two different ones. So, and here it's end if, then end if of this loop. Then come to this condition check. If reading out of range, that means if reading out of range, there's no value mentioned here. That's a Boolean thing. Because here false, false, and here it's true. That's a Boolean thing. For Boolean, you don't say if reading out of range equals true is not necessary. If you just say reading out of range, that means it's true. Otherwise, you can put a that exclamation mark in front. If not reading out of range. So here in this case, if reading out of range is true, that means in one of these cases, right? Call warning display reading. Call warning display reading. So that's another thing like this. Call sensor read, sensor value, something like that, another function. Call, the word call is to call it, it's just lying, but now get it to action. Warning display reading. So reading is like some information. With that, the warning display will take place. Reading out of range equals false. That means again you initialize. Make it original like false. Otherwise, it will go on giving this message all the time. If you don't change it like this. Then for time filler equals 1 to, yes, there's a thing like that what I did earlier. Just counting. But there's nothing underneath to print or to do any process, not there, nothing, no output. So it's just counting. But here I'm not adding one. Why? To time filler. Because for this for loop, this is a pseudocode. For loop is automatic. Incrementing the counter is automatic in for. In while and repeat until and all that, you have to increment manually. Okay. So until end reading sensor, that means when that becomes true. So that part is not here where it is ending. So just have a look now. If the range is high, it will happen here. It will only this will happen. If it is less, this will happen. These two, the reading out of range will get the value true and reading will get the value L. So two different things. If it is not H or L, what happens? From this, nothing will happen because this is checking whether it's more than the maximum allowed, and if not, else if it is less than the minimum allowed. If not, nothing. Just come here and then do these things. This also will not happen, no? Because if reading out of range, that is also still false. Then what happens is, since it's a loop, it will go on like this without anything happening. Without anything happening. Something will happen only when it exceeds the range, the limits, either high or low. Is that clear?
Yes, sir.
Okay. Then the next page. Note the following features of the program. There is an infinite loop. Yeah, we notice that, no, because there are no ending. This until there is a loop, there is a loop here, but until end reading sensor. But that is there's nowhere that variable is getting a true value. Initially, it's made false, and still it's nowhere is it becoming true. Because of that, this is a never-ending loop. Infinite. The loop finishes with another loop that does nothing other than create a delay before the outer loop. That's a delaying tactic. When the sensor reading indicates a problem, the loop procedure to handle whatever notification method is to be used. We saw that here, display warning or something. Following this,
Yeah.
the loop continues, so the Boolean variable has to be reset to prevent the warning procedure being repetitively called. So, as we mentioned there, otherwise it will go on repeating. Because of that, we have to uh, reset. Reading out of range equals false. We have to make it reset. Then an example monitoring and control program. Earlier it was what? Only monitoring. Only monitoring. Here, now we are because you just issue a message only. The humans will take action. For example, a good example for monitoring system is like a patient in ICU. You have seen patients being plugged in with various electrodes connected to ECG and sugar, pressure, heartbeat. All the measurements are done, and if a nurse has to do it, it's very difficult. So many patients, and then going from one patient, timing, every 15 minutes or half an hour you have to do. It's very difficult for a human to do it efficiently. But here, what happens is You can connect 2, 3 patients to these machines at the same time and keep, and the nurse can relax and spend time on more productive things like preparing for something else, looking into another matter. If there is something wrong, the monitoring system will issue a warning, and the nurse will take action, or the doctor, or will call the doctor to take some action. If we give that corrective action to the machine, it can be disastrous. For example, the corrective measure may be giving an injection. So doctors only can decide at that time. You can't give a general thing instruction for the machine to give an injection for this kind of thing, for this particular condition. There are so many conditions and you can't write down all those things, and the doctor on the spot will decide. So that element is there, thinking and taking decisions, whereas the computer just follows the instructions. So here is an example monitoring and control program, both monitoring plus the corrective thing, control. Consider a system which is controlling an enclosed environment. Enclosed environment. The environment has a sensor to monitor a property and an actuator to control that property. The following fragment of code might be used. So a property, now you know that property, these properties mentioned here are the things that are measured by sensors like heat, temperature, oxygen, pH, humidity, pressure, light, sound. All those are like physical properties in the environment which can be measured by sensors. So here is a fragment of code to be used. Now you are familiar with this. In reading sensor is false. Read desired output level. So here from a record in the database stored value, it will read desired output level. Then the loop begins. The never-ending loop begins. Call sensor read sensor value. Something like earlier, same thing. The function name is this, and inside that is a parameter value. Sensor difference equals desired output level minus sensor value. Sensor difference equals desired output level, that is this desired output level minus sensor value. So you take a difference. If ABS, it's like the absolute, like ABS sensor difference, maybe minus, maybe positive, you get the absolute difference, less than desired output level divided by 100. Then sensor difference equals 0. Don't memorize these things because these are just uh, facts, samples.
Okay, sir.
Yeah, otherwise there no meaning in that. Maybe the percentage or whatever, depending on the requirement. So if this is less than that, then sensor difference equals 0. So you make it 0. And if sensor difference greater than 0, then you have something to do. Then actuator adjustment factor. So there's another variable which is not mentioned here. Actuator adjustment factor. So like open this way, that left or right or up or down. Sensor difference divide by desired output level. Then the adjustment direction equals up. Call that is to move up, maybe, possibly. Call is another function we are calling activate actuator. So that's another segment of program. Adjustment direction, comma, there's another uh, parameter. There are values. Actuator adjustment factor. direction and factor. Direction and factor. Just a second. Then if sensor difference is less than 0, then it's down. Earlier we did, if it is greater than 0, the direction is up, possibly a movement upwards. And here if the difference is less, then the movement is down. So the same things happening here. For time filler equals 1 to 1 lakh or 1 million or whatever, 1 million. N4, right? That's a loop until N reading sensor. So due to something this happens, switch off or something like that. Otherwise, it will go on doing this. So here what happens is there's something happening also. No? Now earlier one, it was only issuing a warning. Yes, issue a warning. But here the actuator is doing some work. So actually the like a robot or some like as I mentioned earlier, opening the sprinkler to spray water or something like that actually happening, controlling. Any questions up to that?
No, sir.
Right. Note the following features of the program. A procedure is called to activate the actuator only if the sensor reading shows a significant change. Okay, we noted that. The code will only work properly if it can be guaranteed that the activation of the actuator has caused a change in the property before the sensor reading in the next iteration of the loop. So every time the actuator does some work, the sensors are change. Otherwise, there is no use. The actuator, the action of the actuator will change the property in that environment there. Maybe the temperature, maybe the pH value, humidity, whatever it is changed. In a loop, it is done. Now we are going to separate a different one, bit manipulation. The two fragments of code in section 22.02 have a direct call to a procedure to take some action. A slightly different approach would be to set values of Boolean variables, values for Boolean variables subject to what the sensors detect. For instance, if a controlled environment had two properties to be monitored and controlled, four Boolean variables could be used. Values could be set by assignment statements such as, because true, false, true, false. So you have to have four for two variables. Uh, yeah, for instance, if a control environment had two properties to be monitored, we need four Boolean variables could be used. Values would be set by assignment statements such as, if sensor different greater than 0, then sensor 1 high flag equals true. There are two properties, then there are two sensors. What are they? Sensor 1 and sensor 2. So if the difference is greater than 0, then we put this flag. This is a flag. Sensor 1 high flag is true. If it is less than 0, then the low flag is true. Same way, the other two also true. Here, true, true. Yeah, the flag, the high flag and the low flag is true. The second sensor. Another part of the monitoring and control program would be checking whether any of the four flags were set. The machine code for running such a program could use individual bits to represent each flag. The way that flags could be set and read are illustrated by the following assembly language code fragments in which the three least significant bits, position 0, 1 and 2 of the byte are used as flags. Let's see. LDD0034 loads a byte into the accumulator from an address. So in low level programming like assembly language, this is how it is done. Loads a byte into the accumulator from an address. Accumulator is a register where it is used for doing the processing like additions, divisions and all that. So load, then and to that one, and uses a bitwise AND operation of the contents of the accumulator with the operand to convert each bit to 0. That means AND mean, let's take an example. No, we'll do this first and then I'll show you the example. So then afterwards it says store. That is stores the all altered byte in the original address. The original address is 34 and that result is stored in this. After ending this, called ending and bitwise AND operation. That means this bit and the byte, this byte has a value, it's not given here. With that bit, it's in the accumulator. With that you AND it. This 0 and what is the other one? So all will be zeros, no? AND operation. If it is only one and
Yes.
one only, one and one only, it will become one. So then again load 3 4, then users now this time XOR. So you just add one to that. Uses a bitwise XOR operation of the contents of the accumulator with the operand to toggle the value of the bit stored in position 0. This changes the value of the flag it represents because this will change. No? If it was 0 there, it will become 1. If it was 1, it will become 0. 1 and 1 is 0 like that. But XOR is, remember, no, 1 no 1. 1, sorry, yeah, 1 or 0 will be 1. 0 or 1 also will be 1. 0 and 0 is 0. 1 and 1 is also 0. This is exclusive OR. If you remember our logic gates and the truth tables. So uses a bitwise AND operation. Now this time again AND, like this AND operation of the contents of the accumulator with the operand to leave the value in position 1 unchanged, but to convert every other bit to 0. So that value in position 1 unchanged. The position 1 will not change, but all the others will change. Every other bit to 0. All the others will become 0. The subsequent instruction can now compare the value of the byte with denary 2 to see if the flag represented by this bit position is set. And again, store 34, the result, LED 34, OR. Again, you are doing OR. Uses a bitwise OR operation of the contents of the accumulator with the operand to set the flag represented by the bit in position 2. All other bit positions remain unchanged. So it's a little bit complicated, but when you do over and over again, it will become clear. So as I promised, now we have come to the end. It's also a very short chapter. As I promised, I'll do the demonstration of the bitwise and all that operation. So today, 14th, yeah, doing chapter 22. And the attendance. Here's an example. 1 1 0 1 0 something like that. 2 4 6 7 8. The very first one was, let's take all or operation. Or with, we can give another number like 0 1 0 1 0 1 0 2 4 6 7. Because of this leading zeros, I had to put a single quote mark. 1 2 3 4 5 6 7 8. 4. Yeah. If you OR this, the result will be, what will be the byte here? You have to start from the right always, just like any other addition or multiplication. Even for this operation, bitwise, this is called bitwise operators, right? So then 0 or 0, bitwise, one bit at a time. That's the meaning, right?
Oh,
So 0 or 1 is
1.
1. Very good. Then 0 and 0, no? The second bit.
0. So
0 or 0 is 0. Then 1 or 1 is
1,
0, 1.
1, 1, 0.
Okay, coincidentally, all the things have come. Is that correct?
Yeah.
2 4 6 7. Yeah. Then if we take, see, the difference is only this one, no? Only this. Take the original one. Generally, you don't compare both. You just take the original one, and this is operator. Yeah, or operator. The difference between this and this is just that last bit. Now let's take AND operation. 0 1 0 1 1 1. Ending with 0. You just do like this. Now, when you do it, the first bit 0 and 1 is 0 and 1 is 0. Okay? Not all this time. Then the second bit is 1 and 0. Again 0. Third 0. All the others 0. No? It's not addition, remember. Right. You saw that. So it's a new thing for you, no? That we are not done things like this. When you AND, it can be another number, big number also. But I just showed just adding one AND. Supposing it was random. 1, 2. This was to be done. The first bit is 0. Second bit, how much is second bit when you end? Shahid, are you there?
Yes, sir.
Huh? Are you not sure of this second bit? Meaning from
It's just N
first bit,
with this
more, least
zero.
second bit.
Zero, zero, zero,
Second bit is
zero,
also
one.
0. Third is 0. Fourth is 0.
Fourth is zero. Fifth
Fifth is
is one. And then the rest are zeros.
no. Fifth is not 1.
Then?
Fifth bit both are 1, no?
Yeah.
So 1 and 1 is 1.
Yeah.
It's 0. Oh, no, no, I'm sorry. I'm sorry. I'm sorry. You said 1. I made a mistake. Yeah, okay. All the other zeros. Correct.
Yeah.
2, 4, 6, 8. Yeah. So that's easy, huh? Then if you get EXO, 1 or 0.
So fake. So I would be, we need a second bit also, yeah.
The numbers we give. I will, yeah, I'll put 1, 1, 1, 0, 0, 0, 1, 1. Let's see what happens to the first bit.
Um,
1 EXO
zero.
1. Huh?
So zero,
Yes, correct. 0, 1. 0 EXO 1.
one,
1. Then third bit
zero,
is 0 EXO 0, 0. Okay.
then one, one.
1. Another one.
Yeah.
Yeah,
And then another two ones.
two ones. All right.
And then zero.
Last one. Very good. So this is used in several places. Like I wonder whether you remember we did whose complement once
Yes.
whose complement the BCD binary coded decimal. They also we came across this.
Yeah.
We have the summary is here. A monitoring system requires sensors. Before that, do you have any questions regarding the last one we did
No, sir.
or anything? No.
No, sir.
Right. A monitoring system requires sensors. A monitoring and control system also requires actuators. So you can think like sensors, the input devices, and the actuators are the output devices. Those are the differences between the normal computer systems. In normal computer systems, you have the input devices and the output devices. So the common one is the processor. In both systems, the microprocessor or the CPU is there. In a computer and in control system, the processor.
Yes.
Second point is a program used for a monitoring and control system has to operate in real time with an infinite loop that accepts input from the sensors at timed intervals. Okay, we saw that. Program transmits signals to the actuators. The values received from the sensors indicate need for control measures to be taken. Then bit manipulation can be used within an assembly language program to monitor or control devices to see whether the temperature, I mean the flags are set and all that to check Boolean values. Now these things from this you have to remember the five things. Like sometimes you get a question asking a light sensor is used for a burglar alarm, maybe some oxygen sensor for an aquarium, pH sensor humidity sensor in a greenhouse, pH sensor in a water, in a river to see whether the river water is polluted. Various systems are there. Right? So all these systems have five things in common. If you remember that, you can score marks to a certain extent. What is the first thing? The sensors and sensor, analog signal to a processor, microprocessor. On the way, the analog signal is converted to digital. So analog to digital, the ADC device is necessary. It's like an interface. Then what happens is the processor will compare with the stored values. Then take a decision and issue the if there is any change or if it is exceeded the range, then it will issue a warning or control measures. And those will be issued in digital format. In order for the actuators to carry out those instructions, they need analog signals. So the reverse of ADC takes place. DAC, which means digital to analog signals. So those five, if you can remember, you can make up any question about control systems. You can construct the answer. So here are some exam style questions. A zoo reptile house has 16 tanks which accommodate its reptiles. Each tank has to have its own microclimate where the appropriate levels of heat and humidity are crucial. The zoo implements a computer system which supplies the conditions in each of the tanks to a terminal in a central area. Warning messages are flashed up on the screen if any condition arises which requires the intervention of a zookeeper. So here also these are like monitoring and the control is done by the zookeeper. State the name of the type of computing system described. Monitoring. Huh? State two items of hardware which need to be present in the tanks for this system to function correctly. State two items of hardware which need to be present in the tanks for this system to function correctly. Can you name? Read the question and
Mm,
what is it monitoring in the tank?
Thanks. Yeah,
The
so
tanks.
the reptile.
Tiles to survive. There are
Yeah,
what is needed? What is the property that should be monitored?
heat and humidity.
Heat and humidity. Those two things have to be measured and monitored. So you can say
Yeah.
what is the answer to the question? Hardware, the two items of hardware, you have to say heat sensor, humidity sensor.
Oh, okay. Okay, okay.
Those are the yeah.
Yeah.
This is the polling routine. Polling means like looping thing. Polling routine which is used to run the system indefinitely, like an infinite thing without end. Repeat for I equals 1, 2. So we have to fill up no? In the pseudocode that you can do when you're free. I have put this as an assign. No, not it. I think. Yeah, I'm preparing it. I'll put it as an assignment
Okay.
and then can do it. So any questions or you want to discuss something because
Sir, I might not be able to attend all the classes next week since I have exams on the 20th
right.
and the 22nd
So the
and
others
the 23rd.
till 23rd. So
Because I'm not
these,
too sure about Siobhan,
uh,
but I have exams and I have exams 20th to 23rd.
right. So is this method okay for you? Can you catch up later with this lesson? I mean,
Yes, because you upload all of them.
yeah, it's no problem. No?
I can, yeah,
Yeah, if you need any clarifications, you can always make. And also,
yes.
you can put a forum to discuss among yourselves. What about the others?
Okay, I'm not too sure, sir. I haven't spoken to them recently.
So that's the end of the
Okay,
lesson. Next time we have to do chapter 23. Uh, that is, yes, tomorrow. So if there are no questions, we can stop now. No questions?
okay. No, sir.
So thank you very much for joining. See you tomorrow.
Okay, thank you, sir.
Bye. You're
God
welcome.
bless.
God bless
Bye.
you. Bye.